Hey folks, what's up? I'm glad to share the SIW resonator cavity design with you guys in this video. In last video, we demonstrated some basic principles of a substrate integrated waveguide design, such as the determination of a via pitch and via diameter. We can short the both open ends of the substrate integrated waveguide by metal vias to construct a SIW resonator. Today, I will show you how to do this. Okay, let's start. Before we start the design, I developed a tool which can help us design SIW cavity. Its interface looks like this one. And once we input the frequency, the substrate permittivity, the SIW width, length, their diameter and pitch, it can help us calculate the effective length, effective width of the cavity and the guided wavelength in the SIW. We can get the parameters of the cavity. Okay, so let's try to use this SIW design helper to design a SIW cavity resonator working at let's say 10 gigahertz. So we just input some key parameters here. We set the width to be 12 millimeter. The thickness is 1 millimeter. The length is 26 or something. The permittivity, some Rogers substrate we used. I commonly used the one with a permittivity around 2.94. The working frequency, as we said, let's see, 10 gigahertz. So the via diameter, we just set it to be 0.4, and the pitch is 0.65. I set this pitch as for some reasons. First, we need to identify what is via pitch. Via pitch is the distance between two vias from center to center. And I read some literature. They require that the ratio between via diameter and via pitch should be, or they recommended it to be in the range of 0.5 to 0.8. So let's set the via pitch to be 0.65. Then we can use this user interface to calculate other key parameters. We get the guided wavelength as 26 point something, and the wavelength in the media with a permittivity of 2.94. It is, we can see it is 17.5, and the effective length and the effective width of the SIW, they are here. And another thing we have to mention is that once we shorted a SIW at both of its open ends, this can be worked as a cavity resonator. But if we want it to work as cavity resonator, there are some special requirements. The first thing is that the effective length of the SIW should be multiple times of half guided wavelength. Another requirement is that the width of the SIW should be larger than half of the wavelength in the media, but smaller than the wavelength in the media. So we need to change this length a little bit. The first is we noticed that the guided wavelength is 26.25. So if we want the substrate, but the effective length of the SIW is just 25.7. So it's it's close to 1 times of a guided wavelength, but it's still a little bit shorter. We need to change this substrate length so that the effective length of the SIW can be changed. Let's set it to be 26.5. Okay, we calculate again. We can notice that now the effective length of the SIW is 26.23. It's close to the guided wavelength, which is 26.2 around 5. So we change this a little bit larger. Then we try to calculate it. Okay, it's too large. Maybe just the 26.5 is good enough. So we use these parameters to help us design a SIW cavity resonator. In the CST, we can design the SIW cavity resonator. The first step is just to build a normal PCB board. So in the modeling, we can use this to build the bracket. We can use exit to open the parameter box. We name it as bottom copper, the width. We can use parameters SIW width divided by 2, since we need to give there some space between the via and the edge of the PCB board. We call it as just offset. So this one, since this is a symmetrical one, we can call this also as SIW width divided by 2, but plus the offset. Okay, and the length is just SIW length. This one, okay, divided by 2. This SIW length divided by 2. The thickness is normally, since it's working at a high frequency, the skin depth is really short. And normally the PCB board, the copper on the PCB board is just 5 ounce, so it is 0.17 millimeter. And now we can choose the materials. We can try to find it as a copper and try to load it. Then we got it. We preview it, set the parameter, the width as we said is this 12 millimeter. The offside maybe just 2 millimeter is enough. Okay, this one is also okay. A wrong name here. I need to change the name here. Okay, so the length is 26.5. Okay, let's see. Here is the bottom copper, and we also need the substrate part. Okay, we name it as substrate. The same as we build this copper bottom copper part. So it's also SIW width divided by 2 minus offset. SIW width divided by 2 plus the offset. The length is SIW length divided by 2. And this is SIW length divided by 2. Since we've already have a copper at the bottom, so the start of the substrate should be 0.17, and we cite the thickness of the substrate we used in the SIW design helper. We set it to be 1 millimeter, so the maximum should be 0.17. Since this is, we need to set the materials here. The permittivity is 2.94. So let's try Rogers 65880. Okay, let's try this one. Find the preview. Okay, we got this layer. And another layer is the top copper part. We call it top copper. Top copper. The width same as the substrate. It should be SIW width divided by 2 minus the off side. Same as here, SIW width divided by 2 plus offset. And the length, SIW length divided by 2 minus. This should be SIW length divided by 2. This should be, since it's on the top part as above the substrate, it should be 1.017. The thickness is also the same thing, 1.017 plus 0.017. Okay, the material set is as copper. Preview it, we got it. Okay, oops, there seems something wrong. Let's try it here. Okay, we can change it. Okay. Let's check this one. Okay, there's one more 0 here. Preview. Okay, this is normal SIW substrate. Now we need to do another thing. That is, once the normal PCB board is made, we need to put 2 rows of via at here and here, so that this vias is made by metal. So we know that the metal can reflect EM waves. This top and bottom copper and the vias can limit the EM wave in the substrate to make this PCB board work as similar to the traditional rectangular waveguide. The first thing is to change the coordinates. So we change the coordinate to be here. Then we can start to make a VS. First we call it via right row. So the radius should be as we said, 0.4 diameter, so the radius is 0.2, and the position should be SIW width divided by 2. The V center, we need to let the VS have some distance from the edge of the substrate. Otherwise, there will be some engineering problem. So we set it to be, let's see, half of the pitch. And the via is a through via from top copper to the bottom copper, so it should be minus 0.017 minus 1 minus 0.017. Okay, the via is made of copper. The components, we put them in the vias. Okay, then preview it. The pitch is 0.065. Okay, so let's see, there's some distance from the edge of the PCB board. It looks good. Okay, so we have the first via. Next, we need to have another, there's one row of a via. So there should be another row of via. And we made one more VS. Call it via left. So the radius should be 0.2. The center should be minus SIW width divided by 2. V center should be pitch divided by 2, same as the right via. And the height of the via should be minus 0.017 minus 1 minus 101 minus 0.017. So the material is made of a copper. Preview it. Okay, it looks good. So next step, we need to copy this to VS. We can use transformer and copy it the factor, so the distance in the V direction, it should be equal to P, the pitch. So let's say maybe 20 via is enough. Let's have a look. Okay, 20 is not enough. 46, too much. 45. Okay, maybe just 40. Okay. We have all the vias. So we can imagine that the EM wave in the substrate, it can propagate, but because there's at the top and bottom, left and right, there are metals. These metals can limit the EM wave. So now we build up a SIW. This SIW works as similar to the traditional rectangular waveguide. If we wanted to work as a resonator, we need to short both of its open ends. We can see here, this part is open and this part is also open. We need to use VS to short it. Okay, so let's do this there. Okay, so it's called maybe just there 2. The radius is still 0.2 since this will reduce the fabrication burden. And the center should be C divided by 2. C as another parameter. This is P divided by 2. This is a still through there, so it should be 0.0.17 minus 1 minus 0.0.17. Material is copper. We call these components as BL2. Okay, preview C. Let's see, just maybe set it to be 2, so that we want to short this open end, but we do not want to 100% short it, since otherwise the signal cannot get into the waveguide or the resonator. We need a small slot to not have vias, so the EM wave can get into the resonator from this little slot. Okay, it looks good one. So from here to here, it should have vias to short it. We can copy this vias. This vias, let's transform it, copy it. The distance is still equal to the pitch. The number, let's say 5, 7. Okay, 7 is good. Now we have this part. We also need to short this part. So let's just mirror it. Copy them and mirror them. Copy. So we want to put a mirror here. So the mirror plane normal as U should be 1. Preview it. Okay. Got them. Okay, so we already shot this end. If we wanted to work as SIW resonator cavity, it should be shorted at this end too. So we just copy these vias and move them to here. We can achieve this. So copy them. Now first pick some point. And here. Then we can copy them. Okay, great. We've got this one. We have this cavity resonator, but we can notice that this substrate is too short, so we can change the parameters of the SIW length. This is the great advantage of using parameters. Change it a little bit longer to be P divided by 2. Okay, let's see how it works. Okay, it works well. Now we have a SIW cavity resonator. It should work. We want to simulate it, so we need to put a wave port here and here to exit this SIW cavity. So we need to exit the the SIW. Here we just use wave port. Okay. Length should be 4. This should be okay. Here's one port here. Okay, let's have a look at it. And we can set the frequency 10, since this one works at 10 gigahertz, we set it to be 8. The maximum is 30. Okay, let's run the simulation. Okay, it will take a while to get the results. Now the simulation has done, so we can check the S parameters here. Since we just set one port, we only has one S11. S11. Okay, we can check the S parameters here. We can see it is the first mode, second mode, third mode, fourth mode, and fifth mode. And it's when it is not resonant, the S11 is close to 0. And when it is resonant, the signal S11 can be lower. So I think this is the SIW resonant design. So hope you can learn something from this video. Okay, thanks for your watching. See you guys.